the more larger companies invest in 3D printing, the more we can push this forward. Printing single-story houses, by their 100th house, they've learned a lot more about how to build these.
Yeah, I take the 100th, not the first.
Not the
for
first,
sure.
yes.
Yeah. Welcome to Research Matters, the Cornell video podcast where we speak with the scientists and researchers who are tackling some of the most pressing real-world challenges. I'm your host, Laura Riley. Today we're talking about something that touches every part of our lives, though most of us never give it a second thought: the materials that form the buildings around us, the roads, the bridges, the infrastructure of daily life. Our guest today is Professor Sriramya Nair, assistant professor in the School of Civil and Environmental Engineering at Cornell University. She's an expert in sustainable construction materials, green concrete, and the emerging frontier of 3D printed building materials. Her research at Cornell explores how we can build safer, greener, and more efficiently, and what happens when traditional materials can't keep up with the demands of a rapidly changing world. Ramya, it's so good to have you here.
Hi, thank you.
All right, so I guess we'll start with some very basic questions. Why do the building materials matter, and what should be greener about them?
Building materials matter because of the amount of materials that we use in the world. If you think of construction of new infrastructure in emerging countries or in developed countries, we're still constructing a lot in cities, or a lot of our infrastructure is old and we have to replace them. So the amount of materials we need is astronomical. And of those materials, concrete is commonly used because it is economical, it's really cheap, but it can form any shape that you would like it to take. Mm-hmm. And it's also a structural material. You can build high-rise buildings, you can build bridges, it can sustain a lot of load.
So can you quantify, like, how much concrete do we use?
Yes.
Like in a year, say?
Yes. Emeritus faculty Professor Hoover, he was in civil engineering. In one lecture, he put it this way. He said, if you take all the amount of concrete that we use in the entire world and divide it up to the population, it ends up being that each person is consuming about 4-liter Coke bottles, so if you think of these large Coke bottles, so 4 liters, 4 of them. So 16 liters per person.
Per day.
Per day.
Wow, I'm consuming a lot of concrete. All right, and this is going to reveal my ignorance, but can you just back up and describe what is concrete versus cement?
So cement is a powder. It's manufactured. So we take materials that are in the ground and we heat it up, and then we make this powder where when you mix it with water, there's a chemical reaction that's happening, and it goes from a powder and a liquid-like material with introduction of water to something that's solid and that can take load. Mm-hmm. But we don't build just with the cement paste. We typically add aggregates to them, so rock, sand, and so concrete is a mixture. In its simplest form, it'll have cement, sand, rocks, water. But today's concrete is not that simple. It's a very complex mixture.
So what is not green about concrete as we produce it most of the time?
Yeah. Even though cement is only a small part of the pie chart, it leads to the most carbon emissions. So manufacturing of cement, like I mentioned, you have to heat it to 1400 degrees Celsius. We are also burning calcium carbonate, because of which CO2 is being emitted. So all of it, typically, it again depends on the plant and how they're manufacturing it. But for every kilogram of cement that's produced, we're producing about 0.9 kilograms of CO2. So there's high emissions of cement, but that's just cement. But if you think of concrete, because we're using so little cement, overall, you're not actually placing as much material. So it all depends on how much cement do you have in your concrete. But we have to remember that we do need concrete, though. Just because we think the emissions are so high, we shouldn't stop using it. Because like I said, it's really cheap. It's easy to make it. You can make it anywhere in the world. But there are ways we can do to reduce our carbon footprint. But we shouldn't say concrete is bad because it emits a lot of CO2. Mm-hmm. There's a lot of benefits we get from it as well.
So what are some of the ways that we can reduce the carbon footprint of either one?
Yeah. So the first main thing is the pie chart that I was talking about that concrete is, by changing those percentages in that pie chart, you can change the strength of concrete. So whether it is 20 megapascal concrete or 100 megapascal concrete for high strength, for example. So depending on the application, you need to change the composition of that pie chart. So you have to use a concrete that's specific for that application. So that means that you are using only the amount of cement you truly need for that strength. So if you're always over designing your concrete for like 10 megapascals more than what you need.
Do we do that? Is that kind of a common occurrence that we over-design?
Absolutely. Over-design is very common because that's the easiest way to definitely meet the metrics of construction. So let's say the structural engineer says they want 5,000 psi for a specific structural element. Then just to be on the safer side, the contractor or the ready-mix supplier might shoot for 7,500 psi. So to get to that higher strength, just to make sure you definitely have 5,000. So that factor of safety that we are using ends up being we are over-designing. And the structural engineer might have already over-designed it to get to 5,000. So it's being cognizant of it. So if, let's say we are saying cement, every kilogram is kilogram of CO2 of cement, and that roughly adds up to, we are responsible for 8 to 9% of CO2 emissions worldwide.
Wow.
Yeah.
That is incredible.
Yeah. So that means that if you're using 10% less cement.
That's a big reduction in emissions.
Yeah.
What are the greener materials and what are the sources of those? And are there kind of circular economies where it could be a byproduct of something over here that ends up, that would be in landfill or whatever? I mean, what are the options?
Absolutely. There is a lot of emphasis on, for example, cement, you have to post-process the material or manufacture it at 1200 to 1400 degrees Celsius. You have to grind it, you have to process it. But let's say there is a waste material that you have to process only to 600 or 700 degrees Celsius or 800 degrees Celsius, then you are using less energy to make that material. So typically what we do is previously for durability, we were already replacing cement with partially replacing it. We know if you just use 100% cement by itself, there are some products that form within it that are not very durable. There's like a chemical transformation that might happen, and your concrete might actually be weak. So a long time ago, people figured out that if you replace part of cement with fly ash, for example, it's been a few decades now, we found that it actually makes like a more durable product. So now we're talking about it from a sustainability perspective, but in general, making something really durable so that it lasts a long time, so it doesn't crack, you don't have to replace it prematurely. All that is also green construction. So we already knew that replacing cement partially is important. So with coal plants shutting down, there was worry in the industry that we might not have access to as much fly ash in the future.
So that is a byproduct of the coal industry.
Exactly. So then, from then, we've been looking at, there's a lot of clays, there's things called natural pozzolans like volcanic ash, or how do we process them? Because some of them, if you just mix cement with them, they might not be reactive. So then the science here is, what can we do to these materials, like minimal processing, to make them reactive so that we can replace cement with them? And if you think of it, fly ash is a great resource if you have it accessible regionally. But if you have to ship it from across the country,
and you're adding the cost of that, or the emissions cost of that. Yeah.
Exactly. So then it's all about what kind of landfill material is locally available to you. For example, I visited a site. It's a place called Mineville. So it's like 5 hours up north from here. And they have these huge piles of mining tailings. They used to extract iron ore. So they have this whole amount of material that's in like huge mountain, but it's like a man-made mountain of waste material. So then the question is, can we clean up such landfills and use them beneficially to make cement? So then the question is, what is the composition and how can we, like I said, minimal processing? That is also a way of bringing in new revenue for the counties, new jobs, because you can set up new plants and process those materials.
So I can imagine that persuading the construction industry to adopt some of these new materials may be tricky, just because, I mean, we've seen in recent years horrible failures in terms of bridges. I mean, that Surfside, condo in Florida, and that has caused a lot of kind of retrofitting, or at least kind of hand-wringing about building materials in the 60s or 70s. So are these new materials a hard sell, or are there kind of regulatory hoops that you have to jump through to get them approved?
Yeah. So I think that's a two-part answer. So the first part is American Society of Civil Engineers, they rate all our infrastructure. So every few years, every 4 years, there's like new ranking that comes out for infrastructure. So the bridges we drive on to go from our house to the work, all of them are rated. And in general, most of the reviews for, so that's like dams, bridges, anything that you think of infrastructure, it's like a huge number of categories. Most of them are like a C, C minus. So a
Not too good. Why is that not shocking somehow? Yeah.
But in general, like we need a lot of money for maintaining the infrastructure, and we only have limited resources. So then the question becomes the resources that a county has, for example, what are they going to spend those dollars on? How are they going to prioritize what needs to be fixed? So that's where it becomes challenging to figure out or predict this is the next building that's going to fail, or this is the next bridge that's going to fail. When you have 100 bridges that are all at a C minus, and you only have, let's say, $1 million.
Yeah, what's the triage there? Where do you prioritize?
So that's like the tricky part, because majority of our infrastructure is failing, and we need a lot of maintenance to keep up with that infrastructure. So that's one of the biggest challenges. But you asked a question about what kind of changes are happening in the industry so that we can use more green concrete, for example. In the last 5 years, especially, I would say, there's a huge boom in startups. There is so much innovation that's happening in the space of trying to reimagine what is concrete, like alternative binders, or we've been doing this a certain way, but is there a different way of how do we even make the cement, or what goes into that pie chart that makes concrete? There are significant innovations that have come up in this space, and the industry is changing. There have been some trial experiments to place, for example, Minnesota DOT placed a whole pavement where they used 10 different types of green concretes to understand how different their placements are, how long will they last. Previously, to get to that stage would have taken much longer. But as a community, we have taken on this challenge to make better concrete, greener concrete, sustainable concrete, more durable concrete, to just reimagine what we can do. And there's a lot of changes that have come, and we've embraced it.
So is net zero, is that just a complete pipe dream, or is that a conceivable goal for concrete?
So the Global Cement and Concrete Association has a vision for how do we get to net zero. Obviously, it isn't one thing that's going to get us to net zero. It's a different mindset, and it's also the technological advances that are going to come up in the near future. Like I said, we've invested a lot in new technologies recently. Obviously, some are going to fail, but there are quite a few that are very promising. So if we stay the course and get to the finish line, and we do little, and everything adds up, then net zero is possible. Because right now we are at 10% CO2 emissions, and it is achievable because we are thinking it all the way through, right? From who's producing the cement to who's specifying what type of concrete do we need, how are we making the concrete, and this circularity of how are materials being used and where are they going to end up in the end. So we are keeping that whole thing in mind when we are thinking about concrete. So it is definitely achievable. This is a global problem, and the solutions are also global, and the global community is coming together to solve this problem.
So I know you've done some work in concrete repair and using magnetized, I don't know exactly how to term it, magnetized materials. What does that look like, and how does that solve the problem?
Absolutely.
Or a problem?
Yeah. Like I said, a majority of our infrastructure is failing. Repair is one way to use the least amount of material, because if you have to tear it down and construct again, that's a lot. So in the recent past, we've worked on the concept of adding magnetic particles to the repair materials, because most repair materials, what happens is they are a surface treatment. You can't actually infill the cracks to the depth. Most of the repair happens very close to the surface. So that's good for not wanting unwanted chemicals to go into concrete and, make it worse.
Cosmetically, repairing.
Yeah. But you actually want to improve the strength of your structural element, let's say, because it's load bearing. Then you want to infill it all the way to the depth of the crack. So then we developed this technique where, and sometimes you might only have access to the surface of the concrete. So we developed this technique where you inject magnetic particles with the solution that can heal your cracks. But what it does is you can push the fluid away from the surface. Typically, materials want to go towards a magnet. They attract towards the magnet, but we designed a system such that it can push away from the system, and that way you can infill deeper than you could without the magnetic
So you're pushing
treatment.
kind of with a magnetic
Yes,
force, pushing something, a material in
exactly.
to fill the cracks.
Exactly,
Wow.
yeah. So that's been very exciting to see the potential to fill cracks that would have been harder to fill otherwise.
Wonderful. And I know another big part of the research that you do is in 3D printing. You know, we've all watched those mesmerizing videos on YouTube or whatever of a building being constructed with these big robotic arms. What does that look like, and how does that kind of compare in terms of greenness or sustainability?
So we do have a large-scale robotic arm in our lab too. So when people walk up to it, it's just like amazing. So all the students that are taking classes that walk by the lab, they're just very mesmerized with, whoa, look at that robotic arm. So it has that effect on most people that walk by the lab. And I'm mesmerized by every time we print something new in the lab. So when we think of 3D printing with concrete, all the things we talked about, green concrete and the mixture design, we are applying the same concepts, but it's just that this is a flowable material where the material gets placed through a robotic arm. So concrete can take the shape of any formwork that you place, but here there's no formwork. So that means that's also less waste, because typically formwork is wooden based that might end up in the landfill, especially if you're doing customized shapes for an architectural feature. But now with a robotic arm, you can actually print any shape that you want without any formwork. So this opens up opportunities for example, in our lab, we are exploring infill patterns. Let's say gyroids we worked with. And
is that something that will have more structural integrity because of the kind of crisscrossy shapes?
Yeah. They are basically, like if you think of like a sine curve,
Yep.
it's more like a sine curve in 3D. That's the easiest way to think of
Sure.
it.
Okay.
Yeah. So it's like this wavy structure inside. But what it does is it's really good in compression in all directions, because concrete typically is really good in compression. So we're choosing shapes that play to that strength. Because it's weak in tension, we want to minimize the regions where concrete would be in tension. And wherever it's in tension, we typically place rebar. That's why it's called reinforced concrete. But here in our lab, in the beginning, we were mostly doing unreinforced concrete. For example, we printed steps in our lab. And
I saw those. I saw those on the website. They're very cool looking, kind of cross-sectionally. Yeah.
Yes, exactly. And then we try to use, because arches are good under compression, so all the load gets transferred through the arch. I know the span is small, but it sells the idea that with 3D printing, you can reimagine what structural elements or shapes could look like. So if you think of those steps, we eliminated so much material in the steps by using that shape optimization.
Yeah. But is there more structural uncertainty with 3D printing? And I mean, obviously, you're doing things that are layered, essentially.
Yes,
and
absolutely.
how does that, impact longevity of a building or even
Absolutely.
load?
Absolutely. Those are questions we are all asking. Those are all existing challenges, because the answer is it depends. It depends on your material. It depends on the temperature conditions that day, the humidity, how well it will bond with each other, like the layers that you're placing, or it could be based on the printer setup that you have. So just because I get good printability and good bond strength doesn't mean you get it too, because we are all learning as a community. So we still have to have standards, which is also something a lot of the organizations are working towards, setting up standards, saying that these are metrics that you have to meet with 3D printing, because there's no standards right now. So for printing single-story houses, they're printing larger elements than what's needed to make sure they're strong enough. So let's say if you say, oh, a 4-inch wall is enough, then you're printing a 6-inch wall, let's say. But it's just to make sure that, and also like Icon, for example, they've printed the 100 homes in Texas. And by their 100th house, they've learned a lot more about, how to build these.
Yeah, I take the 100th, not the first.
Not the first,
sure.
yes. No, but the more we build, the more larger companies invest in 3D printing, the more we can push this forward. Yeah.
So I think you recently got a FAST grant for AI and 3D printing. I imagine AI could be employed just to kind of deal with the thorny problems that might crop up in what you just described. How could it help you?
Yeah. So in the past, most of my work is experimental, which means that we never really had that many data points to do AI. I know you can do machine learning and AI with smaller data sets, but that's not what AI truly is for. But now with robotic construction and having so much control over your structural elements and how are you placing them and where are you placing them, we can collect a lot of data. So all of a sudden in my research group, we've gone from we don't have as much data to we actually do have a lot of data. So how can we use this knowledge that we are gathering during printing and after printing to make better informed decisions? And that could also translate to large scale. Like you said, there might be uncertainty and you might not have you're like, I'm printing, but is it the same over here and there? Like
Sure.
quality control,
Would
for
this
example.
be kind of open source so that everybody could contribute data to...
Once I figure out how I can use AI, absolutely. We publish everything, right? So yes, that is the goal. This is my first venture into AI, and that's what a seed grant is, right? Atkinson has been great that way to give
Wonderful.
us opportunities to collaborate across campus with different faculty and, start a new line of research. So I'm very excited to see where that's going to be headed.
So I do want to talk a little bit about funding, because I know that's something that is a challenge, and that we have kind of priority changes that shift our commitment as a country, as an administration for infrastructure reinforcement. How has that affected you, and how are you seeing the way forward?
In the past few years, we have been extremely fortunate as a community where we've seen huge investments from the federal government to support the research that we do, both from longevity, durability, but also reimagining how we make the cement and what do we want to put in this pie chart. So there's been a huge range of thought processes that have gone into from different researchers. So it's like I said, it's we've been very fortunate, and but with the recent changes in the priorities, including me, a lot of people have lost a lot of federal funding. But I truly believe that we have learned some really good ways of making better concrete. It's like the next generation concrete, and there's a lot more to happen in this space. And even though the federal priorities have changed, we need to keep pushing our knowledge forward so that way we don't reverse back to how we did things 15 years ago, 10 years ago. And also with automation and with robotics that are going to come up, there's going to be a lot of changes that happen in the industry in terms of what is feasible. And we need to embrace those changes along with green concrete to make infrastructure better.
So it seems like, is Europe kind of leading the way right now? I know there's that, is it LC3?
Yes.
Concrete. Are there centers in the world where there's real forward movement that we should all be emulating?
Yeah. LC3 is a great example of a material that's been globally accepted and is going to have an immediate impact in the near future, like right now, of how what materials we could put into that pie chart. It's all about that pie chart. And LC3 is just one such example. There is so many other, because they mainly focus on limestone and calcine clays, but there are so many other materials that are really promising and have a good future. Even in the US, we've spent a lot of time, like collectively as a community, on calcine clays, but we're also interested in other material systems as well.
With these podcasts, I love to, if there is something that you can give advice about for home buyers or consumers, is there anything they can do to make better choices in their own lives in terms of building materials or home projects that will move the needle a little bit in terms of in a green direction? Absolutely.
I think the first thing would be is don't be afraid to consume your 4-liter Coke bottles of concrete every day. Because we need it in our everyday lives. Like infrastructure makes our lives better, and concrete is a structural material. It's not just a material that can hold its shape and take load, but it's a structural material that can take significant amounts of load. So if you think from that perspective, concrete has a very important role to play, and it's not that expensive.
So, Ramya, this has been really fascinating. I actually saw you speak about concrete at a bar, at a nerd night at a bar downtown, and I thought, I did not know how fascinating concrete was. So that's why you're here today. Obviously, this is about climate change, but it also hits, home construction and transportation and all of the infrastructure around us. But it really underscores kind of how much innovation is still needed. And the work you're doing is obviously heading us in the right direction there. If you want to learn more about Dr. Nair's work or Cornell Engineering's research in sustainable infrastructure, you can visit nair.cee.cornell.edu. I'm Laura Riley, and we'll see you next time right here on Research Matters.